Bismillahirrahmanirrahim. This is the lecture of the course Fundamentals of Organochemistry. The title of this lecture is The Reactions of Aldehydes and Ketones. In the previous lecture, we have discussed introduction of aldehydes and ketones, nomenclature and preparation of aldehydes and ketones. In this lecture, we will discuss reactions of aldehydes and ketones with mechanism. Reaction at the carbonyl carbon, the elements of hydrogen and nucleophile are added to the carbonyl group. As we have discussed in previous lecture, the carbonyl carbon is electropositive, means there is electron deficiency due to moro-electron activity of oxygen. Due to this electrophilic nature of carbonyl carbon, nucleophile can attack on carbon. Nucleophile attacks on the carbon, then produce oxyanion, and this oxyanion subtract the proton from the medium and gives the final product. Overall addition reaction takes place. Mechanism with a negatively charged nucleophile addition follows a two-step process. Nucleophile attack followed by protonation as shown below. First of all, nucleophile that has a negative charge attacks on electrophilic carbon of carbonyl, and this oxyanion which is sp3 hybridized and subtract the proton on water or medium and gives the final product, and this is the example of addition reaction. The nucleophile may be strong or neutral, or may be lone pair containing or negatively charged nucleophile. This is an example of nucleophilic addition. In this reaction, aldehyde and ketones are treated with sodium cyanide and HCl. In this case, HCl and sodium cyanide reacts with each other and gives HCN, and this cyanide attacks on the carbonyl carbon of the carbonyl carbon, and 5 bond breaks and gives finally cyanohydrin product. First of all, cyanide attacks on carbonyl, then it gives oxyanion. This oxyanion subtract the proton from HCN and gives the cyanohydrin product. In cyanohydrin, the oxygen and cyano group present on same carbon. Cyanohydrins can be reconverted to carbonyl compound by treatment with base. This process is just the reverse of the addition of HCN. The protonation followed by addition of cyanide negative. First of all, base subtract the proton, then negative come back to the carbon, and cyanide blue and give back to the original aldehyde or ketone hydride. The cyano group of cyanohydrin is readily hydrolyzed to a carboxy group by heating with aqueous or base. Further application of the cyanide is easily hydrolyzed to the carboxylic group, and it can be reduced to primary amine easily. These are the two compounds. Liinamarine and amygdalene are two naturally occurring cyanohydrins. You can see the terminal cyano and alkoxy group present on same carbon. And this compound is present in cassava root. And the second compound is the amygdalene. In this case, you can see the cyano and alkoxy group present on same carbon. Both compounds show toxicity in metabolism. These compounds are hydrolyzed to carbonyl compound and HCN, and HCN acts as a toxic product. So you can see cyanohydrin derivative enzyme breaks the alkoxy bond with acetone cyanohydrin, then enzyme converted into acetone and HCN. HCN is a toxic. With some neutral nucleophiles, nucleophilic addition only occurs if an acid is present. In this mechanism, protonation proceeds nucleophilic attack as shown below. When nucleophile is certain, means any lone pair present or negative charge present on the nucleophile, means certain nucleophile can directly attack on the electron deficient carbon of the carbonyl. If the nucleophile is neutral, means negative charge or lone pair is not present on the nucleophile, then it is difficult for the nucleophile to attack directly on the electron deficient carbon. So in this case, first activate the carbon by the addition of proton on oxygen. First of protonation takes place, then the bond between carbon and oxygen moves towards oxygen and carbon bears positive charge. Then the neutral nucleophile can attack easily on the carbon. Here is below the mechanism of such type of reaction. And then nucleophile attack on the carbocation, and then the hydrogen are subtracted by the base, and this is the final addition product. It is important to know that nucleophile will add to carbonyl group. When chloride, bromide and iodide nucleophiles add to the carbonyl, they leave the carbon oxygen pi bond, forming an oxide. Since halogen is a much weaker base than the oxide, form equilibrium favors the starting material, not the addition product. As halogens are weak nucleophile, it is when attacked gives the alkoxyanion. Alkoxyanion is a certain base. It gives a back reaction more powerfully as compared to forward reaction. So overall net results no reaction will take place. Next is the nucleophilic addition of hydride. Aldehyde and ketones with any hydride providing compound reacts, and then protonation form of primary and secondary alcohol gives the final product. The sodium borohydride and lithium aluminum hydride are very good hydride providing reagents. And so aldehyde and ketone reacts with sodium borohydride, lithium aluminum hydride, then gives the intermediate, then protonation occurs and gives the finally alcohol. This is the mechanism. First, hydride attacks to the carbonyl carbon and gives this alkoxy-ion. This alkoxy-ion may attach with the lithium plus, and then this oxygen or subtract the proton and gives the alcohol. Then next is the nucleophilic addition of alkyl group. Aldehyde ketone with either an organolithium or Grignard reagent followed by water formed in the presence of acid. A new carbon-carbon bond is formed. In this reaction, alcohol is the final product. Aldehyde ketones reacts with organometallic compound. Organometallic compound may be Grignard reagent in RMDX or alkyl lithium in RLi or dialkyl preparate or zinc alkyl may be the any alkyl organo compound. First of all, In all these compounds, organometallic compound, alkyl group acts as a nucleophile, and this nucleophile attacks on the carbonyl carbon and gives intermediate. In the intermediate, oxygen attacks with the metal atom. Then further process takes place in the presence of ether and gives the final alcoholic product. In this case, alkyl and hydrogen group acts on the carbonyl bond. Below is the mechanism of the nucleophilic addition of alkyl group. In the mechanism, phenyl acts as a strong nucleophile and attacks on the carbon, and this gives a oxyanion. This alkyl oxyanion is protonated in the presence of ether and gives the alcohol, secondary alcohol product. These are a sample of Grignard reagent. In this case, methyl magnesium bromide. Methyl acts as a proton nucleophile, attacks on the carbonyl carbon and gives the tertiary alcohol. When this tertiary alcohol further processed with sulfuric acid, and this converted into alkene. Alkene may be terminal, may be more substituted. The product may be Hoffman may be says that depends on the condition. But here is a more substituted product is the major product. Reaction at the alpha carbon. The carbon present at the carbonyl carbon and have hydrogen. These hydrogen are slightly acidic, and these proton hydrogen are subtracted by strong base and gives carbon anion. This carbon anion is resonantly stable with carbonyl carbon, and this carbon ion can attack on any electron deficient species, mean electrophile, and will give the product. This is the example of alpha carbon reaction. This reaction is the aldol condensation. In this reaction, first of all, a strong base means sodium hydroxide or potassium hydroxide absorpted the proton from alpha carbon and create negative charge on carbon, and this negative charge attacks on the carbon of benzaldehyde and gives the final product with the removal of water molecule. This is the mechanism. Base absorpted proton. This proton resonantly stable is imine, and this imine attacks through resonantly on the carbonyl carbon, and the oxyanion, and this oxyanion subtracts the proton from water molecule and gives the hydroxide, and the hydrogen is present at alpha position. Due to its alpha position present, and base is also present. The base subtracts the proton from alpha position and water is removed. Finally, a double bond is produced at this point by the removal of water molecule. Alpha hydrogen must be present for the reaction of aldol condensation. Aldehydes and ketones can be similar or different, but compulsory condition is the presence of the alpha hydrogen of any one compound. The aldol condensation may be intermolecular and may be intermolecular. Claden-Schumann condensation is the intermolecular condensation. In this case, the methyl of the acetone absorbed proton by base, and this carbon attacks on the carbon of the benzaldehyde, and it is the final product with the removal of water molecule. And the next example is the intermolecular aldol condensation. Means the aldol condensation occurs within the molecule. In this case, the methyl group is initially converted into enol form in the presence of acid. Then is enol form come back through the resonance, and carbon attacks on the carbonate of the ring gives the final product. Next is the Grignard reaction. In Grignard reaction, aldehydes that does not contain alpha hydrogen reacts with any strong hydroxide base, means sodium hydroxide or potassium hydroxide. In this reaction, two molecules of aldehyde is used. These aldehydes may be same, may be different, but in this case the aldehydes are same. So sodium hydroxide attacks on the carbonyl carbon, and one molecule of the aldehyde is converted into carboxylic acid, and second molecule of the aldehyde is converted into alcohol. Below is the mechanism. In this case, hydroxide attacks on the carbon, and it gives alkoxy-anion. Then oxygen, negative charge on oxygen come back, and hydride removes from this intermediate and attacks on the second molecule of benzaldehyde, and the second molecule of benzaldehyde is converted into alkoxy-anion, and first molecule is converted into the carboxylic group, and second molecule further subtracts the proton and gives the alcohol, and first molecule is converted into the acid. The mechanism may be also as first subtract the proton from the second hydroxyl group, and this oxyanion, and then one of the oxyanion comes back and gives the hydride, and hydride attacks on the carbonyl carbon of second aldehyde, and then gives the carboxylate anion and alkoxyanion both are worked up in the presence of acid, and gives alcohol and acid. The condition of this reaction is there should not be alpha hydrogen. If there is alpha hydrogen present in the molecule, then aldol condensation will occur instead of Grignard reaction. Next is the reaction with amine. Aldehydes and ketones react with primary amine amine, which is called a well-known name with Schiff base. So nitrogen has one pair, acts as a good nucleophile, attacks on the carbonyl carbon. In the mild acidic condition, first converted into carbonyl amine, then water molecule removes within the reaction condition and gives the amine, which is called the Schiff base. Below is the example of the Schiff bases. Mechanism consists of two steps. In the first step, primary amine adds on the carbonyl, while in second step, elimination of water takes place. Here you can see the primary amine attacks on the carbonyl carbon, nucleophilic attack takes place, then obtain this intermediate, which is called carbonyl amine. Then it is protonation takes place of carbonyl amine, then water molecule removed with the help of lone pair of nitrogen gives the quaternary ammonia, and then water will act as a base, subtract the proton and gives the finally amine product. Many amines play vital roles in biological systems. For example, which is synthesized by the rod cells of the eye from one cis retinal and a primary amine in the protein opsin. This is the structure of one cis retinal. This is the only one bond in both structure present, cis double bond, or other bonds. All other bonds are trans double bond. So Ni2 of opsin is attach with the aldehyde group with the present at the terminal and gives the amine bond. Scandamine reacts with an aldehyde or ketone to give an enamine. Enamines have a nitrogen atom bonded to a carbon-carbon double bond. In the synthesis of enamine, initially Schiff base is formed, but due to the positive charge on the nitrogen and this nitrogen for the neutralization, the bond is present on the beta position of carbon. It moves towards the nitrogen, and nitrogen gets the electron pair, and the working product is the enamine. In this case, this is the scandamine reacts with carbonyl compound and gives carbonyl amine, and this carbonyl amine with the removal of water molecule is converted into tertiary nitrogen, and this tertiary nitrogen of the neutralization, the proton present at beta position from the nitrogen gives the electron pair towards the chain, and the bond between nitrogen and carbon moves towards the nitrogen, and nitrogen gets neutralization, and the final product is enamine. This is the example of enamine. The enamine is very good, extensively used in the organic synthesis. It may be used for the protection, it may be used for the any else purpose, but it has very extensively used in the organic chemistry. Because mean and enamine are formed by reversible sets of reaction which can be converted back to carbonyl compound by hydrolysis with NaCN. The mechanism of hydrolysis is the exact reverse of the mechanism written for formation of means and enamine. Due to this hydrolysis nature of enamine, this is used as a may be used as a protectant in the organic synthesis. Next is the Wittig reaction. The Wittig reaction uses a carbonyl nucleophile to form alkene. In this reaction, the carbonyl compound is converted into alkene party through the process of Wittig reagent, which is also called RÚLi. This below are the example of Wittig reaction. In this case, carbonyl compound reacts with Wittig reagent, and the alkyl groups attached with the phosphorus is replaced by the oxygen in the carbonyl compound. Means whole group alkyl group present with phosphorus is will attach with the carbon of carbonyl and give the alkene product. These are the examples. The Wittig reagent is an organophosphorus reagent. A typical Wittig reagent has a phosphorus atom bonded to 3-phenyl group plus another alkyl group that gives a negative charge, such as you can see in our above example. Phosphorus already attached with 3-phenyl, and then fourth one is the alkyl group. The fourth one, which is attached with the, will act as a alkyl group, as a nucleophile group. This is the structure of Wittig reagent, and it is abbreviated as it is a LIAIH. In a LIAIH, positive plus and negative charges on adjacent atoms. A Wittig reagent is an LIAIH, a species that contains two oppositely charged atoms bonding to each other, with both atoms having octets. Phosphorus LIAIH are also called phosphorians. Since phosphorus is a secondary element, it can be surrounded by more than 8 electrons. Thus, a second element structure can be drawn that places a double bond between carbon and phosphorus, which is is shown below. You can see the carbon and phosphorus are attached to double bond. However, note that in one resonance structure, the carbon bears a net negative charge, making it nucleophile. This is the preparation step of Wittig reagent. You can see the triphenyl phosphine reacts with alkyl halide and gives a phosphonium salt. And this phosphonium salt, in the presence of a strong base, and strong base subtract the proton and LIAIH. The typical strong base is the butyl lithium. This is the example of the preparation of the Wittig reagent. This is a mechanism of Wittig reaction. The LIAIH carbon attacks on the carbonyl carbon, and this gives the alkoxyanion, and this alkoxyanion forms the four-member ring with the phosphorus, and this four-member ring is called oxaphosphetane. And then internally bond moves within the cycle and gives the alkene and triphenyl phosphine oxide. So in this way, the oxygen of the carbon is replaced with the alkyl groups that attach are present in the Wittig reagent. One limitation of the Wittig reaction is that a mixture of stereoisomers sometimes forms when LIAIH reacts with the aldehyde or ketone. Then the resulting product may be cis or may be trans, but there is chance of both isomers, but the stable product means trans isomer is the major product. The Wittig reaction has been used to synthesize many natural products. This is the example of natural product. In this case, you can see one right side shows the LIAIH, left side the aldehyde. Both react, and final product is the E-alkene. The resulting product is beta carotene, which is present in the carrot. The most stable E-alkene is the major product in this Wittig reaction. So the trans alkene will be the preferred or major product. Next is the formation of hemiacetal, hemiketal, acetal, and ketal. When one alcoholic group adds on the aldehyde, then it converted into hemiacetal. In hemiacetal, you can see one alkoxy group present and one free hydroxyl group present. When this hydroxyl group is replaced by a second alcoholic group, alkoxy group, then it converted into acetal. Similar case with the ketone. You can see alcoholic group is introduced in carbonyl carbon and gives the hemiacetal. In hemiacetal, one is the free hydroxyl and one is the alkoxy group present. And then if second alkoxy group is introduced at the place of free hydroxyl group, then it converted into ketal. This is very good used in the organolithium. These are used for the protection of the groups, and at the end of the required target synthesis, these are easily removed back to the carbonyl compound. Below is the mechanism of the hemiacetal, hemiketal, acetal, and ketal. You can see over here. This is the intra-cyclization, intra-hemiacetal formation. In this case, the hydroxyl group attacks on the carbonyl carbon and gives the hydroxyl group and ether moiety. The ether, which is the oxy, and this is contain free hydroxyl group, mean one free hydroxyl group present. Due to this, it is hemiacetal. This is the sugar moiety, and it is cyclized with the aldehyde and gives the hemiacetal. You can see the below hydro and hydroxyl bond in the below carbon. One oxy present, which is highlighted by green, and one hydroxyl group present. So this is the hemiacetal group produced in the cyclization. Cyclic acetal are often used as a protecting groups, and below example are the ketone formation. In this, hydroxyl group attacks on the carbonyl of the ketone in the presence of acid, and it is converted into dialkoxy. This is the example of cyclic ketone, and below example are also the example of ketone formation. These are the collectively examples of cyclohexane. In this example, combine the collect all the type of reaction with the cyclohexane in one slide. First reaction is the reaction of hydride, and this cyclohexane is converted into secondary alcohol. And the next reaction with the organometallic compound, mean Grignard reagent, alkyl lithium, etc., and it processes with the presence of acid and gives the tertiary alcohol. Then a reaction with cyanide and gives the cyanohydrin, and next reaction with the Wittig reagent and gives the alkene, and next reaction with the primary amine gives the amine reaction, and next reaction is the reaction with secondary amine and gives the enamine. At the last, the carbonyl reacts with the alcoholic group in the presence of acid, gives hemiacetal or acetal or ketal group. If you have any question regarding this lecture, you can ask through this Google classroom. Thank you.